Welcome back to this week's algebraic graph theory seminar. Today we have Gabriel to talk about how to optimize sums of eigenvalues.
Thanks, Tina, and thanks the organizers for the invitation. So today the talk is not about quantum logs, as it's usually the case with my talks. Today is about one of my other research interests, which is basically on the interplay or between eigenvalue bounds and semi-definite program, right? So if any of you has ever worked with, I don't know, spectral graph theory, you've seen lots of papers that derive bounds to graph parameters using eigenvalues. And these eigenvalues are typically chosen to be the eigenvalues of either the adjacency matrix, a Laplacian matrix, or some other matrix that encodes adjacency in the graph, or some combinatoric information. However, it's typically the case that you can still tweak some of the entries in your matrix, usually by whatever needs to be zero remains zero, but the entries which are different than zero, you can typically have some freedom. And you still get some eigenvalue bound, but the eigenvalues now are of a different matrix. And therefore, you have a sort of optimization problem in which you're asking what is the best adjacency matrix for your graph that still conveys some combinatorial information, but that gives you the strongest eigenvalue bound. This became a field of research back in the 70s when Lovász introduced the Lovász theta number. Well, he called it the theta number. Now we call it the Lovász theta number of the graph, which basically bridges a little bit of these two things. I mean, you have semi-definite programs, which are usually one of the best tools we have to optimize eigenvalues, because eigenvalues can be written as solutions of semi-definite programs, and spectral graph theory, right? And I will very briefly survey some of this connection, and then I will start talking about some of the new things we are looking at. Okay, so throughout the talk, this will be my notation. I will have a graph G, sorry, Chris, adjacency matrix, typically A, and I will be expressing the spectral decomposition of the matrix with this notation, where here, for today's talk, I will be allowing my eigenvalues to be, all of these eigenvalues have multiplicity 1, but they could be repeated, right? So some of these things could be qualities. And usually, well, I will be always assuming that the eigenvalues are ordered from the largest to the smallest, okay? So this is just the standard thing. And this is one of the oldest, and certainly, if not the most famous, one of the most famous results that associates eigenvalues with combinatorial information of the graph. So Hoffman proved back in the 70s that the chromatic number of the graph is lower bounded by 1 plus this ratio, okay? This is met with equality, for example, for bipartite graphs. Because if the graph is bipartite, this thing here on the bottom is equal to lambda 1. Therefore, this thing here is equal to 2. And of course, the chromatic number of a bipartite graph is equal to 2. Okay. And this is also met with equality for the complete graphs and for several other classes of graphs. So this is not this is an interesting bound. Okay, of course, there is no hope that this would ever be a good, efficient way to approximate this number well, because this number is NP hard to approximate. Okay, so, but this is something, and this is a nice, interesting lower bound. And also, when equality holds, it carries a lot of extra information. So if the interplay between eigenspaces and combinatorics in this graph. Okay? Now, in his proof, original proof, you study it and you realize that at some point, actually, what Hoffman does, he writes this. He says that if m is an integer which exceeds the chromatic number, then this sum here is less or equal than 0. So what is this sum doing? It's getting the largest eigenvalue, then the smallest, then the second smallest, and so on, all the way up to the m-1th smallest. And this is saying that if m exceeds the chromatic number, then this sum is less or equal than 0. Okay. And then basically in his original proof, he now comes here, replaces all of these guys by copies of the smallest. So he makes this side even smaller because he's replacing a bunch of eigenvalues by the smallest eigenvalue. And then there are m minus 1 eigenvalues here. So there's m minus 1 times this guy. And then you rearrange and you get that m is greater or equal than the ratio. And this is true for all m which exceeds the chromatic number, therefore is equal to the chromatic number. So you can simply put the chromatic number here and make it go. Now, why does this make sense? Well, this sum here kind of wants to be positive, right? Because this eigenvalue superdominates the other eigenvalues of the graph, typically, if your graph is random, for example. So this is a positive number. Recall our diagonal is 0, right? So it's the adjacent matrix of the graph. This is negative, but it's not too negative compared to this guy, unless, of course, the graph is bipartite, in which case everything is following. And then you start adding a bunch of negative guys until finally you get to something smaller or equal than 0. Okay, so this is a process that makes sense. You're basically asking how many negative eigenvalues do I need to use to compensate for this large positive eigenvalue. Okay. Now, this proof relies only on the fact that the entries which do not correspond to edges are equal to 0. So diagonal entries have to be equal to 0, and off-diagonal entries that do not correspond to edges have to be equal to 0, and that the matrix A is symmetric. So if instead of the adjacent matrix, I go there, I look at the ones, and I replace the ones by any other entries, as long as my matrix remains symmetric, the same proof works. Okay, so now, instead of simply asking, starting with the adjacent matrix and looking at this sum, I can ask, what is the best choice for an adjacency matrix that will give me the largest m here, right? Because what do I know? I know, of course, that if the sum is positive, I have a lower bound to keep to the chromatic number. So what is the best adjacency matrix that will allow me to go as far as I can, still having a positive sum, and therefore well lower bounding the chromatic number? Okay, so we wrote a paper now, myself and two co-authors, Marcel and the student Raphael, and we decided to call this parameter h of g, h of course referring to Hoffman, because we couldn't find a definition for this parameter anywhere else. But please, if any one of you knows that this has already been defined, we would like to further discuss with you guys. But anyway, so h of g is the minimum value of m, so that for all adjacency matrices, this thing here is less or equal than 0. Okay, it means that if I get one unit smaller, there exists an adjacency matrix that will give me a positive sum, and therefore this thing is going to be a lower bound, strict lower bound to key. Okay, and therefore h of g is a lower bound to key. So the minimum value of m that will allow me to say that this sum is always non-negative, is always non-positive, sorry, for all adjacency matrices. Okay. Now, this of course raises two questions. The immediate one is how to compute this parameter. I mean, is it computable, and how to do it? I mean, there is something weird here with this for all. I mean, you have to come up with a good strategy because you cannot simply research, extensively research all adjacent matrices of a graph. Okay. And then there is also an interesting set of parameters associated with the chromatic number with optimization. So we know that the click number of the graph is always less or equal than the chromatic number of the graph. But between these two guys, there are a bunch of other parameters. One of them is the famous, that I will discuss in a second, Lovász number of the complement. It sits between the click number and the chromatic number. And then between the Lovász theta of the complement and the click number and the chromatic number of the graph, there are also other parameters. For example, I listed two there. The famous fractional chromatic number, studied for at least some 50 years now. It's the optimum of the linear program relaxation for the click number of the graph and also for the chromatic number of the graph. And recently, a associated parameter, the quantum chromatic number, has been defined, and it also sits between these two guys. And then, of course, it makes sense for us to ask where exactly this h of g would sit here. I mean, it lower bounds this guy, but where in this chain of parameters? Or can we actually determine where it sits in this chain of parameters? So, for example, it's been proved that between these two guys, you cannot compute efficiently a graph parameter unless p is equal to np. So, for example, if we could prove that this guy sits here, then we would already know that it's difficult to compute this guy. Or if we prove that we can efficiently compute this guy and place it here, we are proving that p is equal to np, but we're not trying that. Not today, at least. Okay. On the other hand, Hoffman's, and I will discuss this in a second, Hoffman's lower bound to key is very, very, very well associated with this guy. So it makes sense to wonder if this has anything to do with the Lovász number, right? The Lovász theta number. So what is this connection? So it's easy to see that this h of g that we are defining is always going to be greater or equal than 1 plus the ratio of the largest eigenvalue of z and minus the smallest eigenvalue of z for all z, which is an adjacency matrix. I mean, we are basically playing the same game here, right? We will be starting with an adjacency matrix z, writing this sum, replacing all of these guys by the smallest eigenvalue, and then basically we can conclude the same thing. We can conclude that h of g is always greater or equal than this guy. And the result from 1979 due to Lovász is that optimizing over this ratio, optimizing overall adjacency matrix, optimizing this ratio overall adjacency matrix actually gives something which is computable, efficiently computable up to precision. Okay, so Lovász showed that if you decide to, I don't know, vary your matrix, your adjacency matrix over all possibilities, and maximize this ratio, this is going to be equal. So this thing written here is a semi-definite program. It's a maximization or minimization of a linear function. This is the inner product of a variable matrix X with the all ones matrix J. So you're maximizing a linear function subjected to linear constraints. I'm simply saying that certain variables of this matrix X are equal to things, or less or equal to things, or greater or equal to things. And here I have a quadratic constraint, but it's actually a nice quadratic constraint, which is a semi-definite constraint. I'm forcing my matrix X to be positive semi-definite. Now, this falls into this big realm of conic programs, but fortunately, the cone here, which is the cone of positive semi-definite matrices, is a very nice, well-behaved cone that you can easily treat it. So there are there are efficient algorithms that allow you to compute this. Okay. So the sort of like for the purposes of this talk, the impressive result is that maximizing this function, which is definitely not a linear function, right? I mean, if I start with Z and I add the matrix W, certainly this is not going to behave in a linear manner. Maximizing this nonlinear function is equal to a semi-definite program, and Lovász called this optimum here the var theta number of the graph, actually of the column. So basically, because this number is an integer, it follows immediately that, well, this number is always greater or equal than this thing for all z. The optimum over this ratio is the Lovász theta number of the complement. So it kind of follows immediately here now that, well, there's some, well, details to check, but nothing complicated. It kind of follows that this guy is always greater or equal than the ceiling of the Lovász theta number of the complement. And the first question we had was whether or not this was an equality. I mean, it could be, and it isn't. Okay, so this was actually the first question that motivated our research. Okay. So, any questions at this point? So what is that fractional chromatic number that I mentioned? So the idea here is that imagine that you're trying to color your graph, right? So you want to put colors on the verses so that neighbors get different colors. Now, imagine now that you're allowed to put fractions of colors, okay? So each vertex has to be fully colored, meaning that the sum of the fractions have to be equal to 1. Instead of saying that a vertex is red, a vertex is yellow, you're allowed to say this vertex is half red, half yellow, okay? But you still want to enforce that neighbors don't get fractions of the same color, okay? So you do not want to allow conflicts at all, okay? And then this is the idea. So this key F is the minimum sum of fractions over all possible fractional colorings of your graph. And this number is, of course, upper bounded by key, okay? Because any coloring is a fractional coloring, but here you're allowed to do better. And there you see an example. You have C5, the cyclone 5 verses. Its chromatic number is 3. You cannot color this graph with 3 colors, but you're allowed to fractionally color it so that the sum of the fractions is the sum of the weights is actually equal to 5 halves. And how do you do that? Well, I use these 5 colors that I didn't use colors, so the numbers, right? So you color these verses with the numbers, and you put weight half for each color. So each vertex is going to receive half a color, okay? And I'm using 5 colors, each one with weight half. So my fractional chromatic number is 5 halves, which is smaller than 3. Okay, so this is an example of a fractional coloring of your graph. The other parameter that I mentioned, the quantum chromatic number, now instead of each vertex receiving a fraction of a color, each vertex is receiving a projection that sort of like represents a color in a sense, okay? And for the fractional chromatic number, you wanted the sum of the fractions to be equal to 1 at each vertex. Here you want the sum of the projections to be equal to the identity matrix. And you want neighbors to get orthogonal projections for each color. So I'm gonna have at my disposal, I don't know, k colors, and to each vertex, I'm going to allow this vertex to use a projection matrix related to a particular color. Okay, so each vertex has to be fully colored, so the sum of the projections for each vertex has to be the identity matrix. But if you look at neighbors, the projection this particular neighbor receives for color red has to be orthogonal to the projection this other guy received for the same color. So this is the sort of like the coloring constraint. And then this this quantum chromatic number is the minimum number of colors that you need to be able to do that. And this is not just an exercise in, I don't know, linear algebra. This parameter actually comes with a very nice motivation. If you have questions about this parameter, you are free to ask David, which hopefully is here in the audience. David is if you think this quantum chromatic number is nice, ask him. Okay, or Maria. I think Maria has also done work on this quantum chromatic number. So anyway. And as far as I know, actually, the relation between the fractional chromatic number and the quantum chromatic number is not known, or perhaps it's known that there are graphs for which you have all sorts of different relations here. But both of these numbers, they lower bound the chromatic number of the graph. Okay. Now, Wokshan, Elphig, and Darbari in 2020, they showed that this H of G, as we define, lower bounds the quantum chromatic number of the graph. And I said that we are coming up with this notation because actually in their paper, they did not define a a letter to mean this thing. They simply show this for the adjacency matrix, and they, in a paragraph, they said, okay, the same proof works if you replace adjacency matrix for any other matrix. Okay, so we're observing that this fact is true. It follows straight from their work. And their proof uses interlacing plus a technique that comes from I guess from some uses in quantum graphs or quantum linear algebra, which is called pinching. So they have this very nice proof that the minimum m, so that for all adjacent matrices, this thing here is less or equal than 0. This actually lower bounds the quantum chromatic number of the graph. Our main result is that this parameter also lower bounds the fractional chromatic number of the graph, which is a more studied and more, more understood parameter in general, right? So we tried to show that this h of g is equal to the ceiling of Lovász theta, and then when we realized that that could not be really true, I mean, there was no reason to believe that was true, then we said, okay, so let's at least try to show that it's upper bounded by something better than key. It was actually after we showed this that we realized these people had already worked with this parameter and showed for the quantum version. Okay. So let me now point out some connections between the combinatorics and the optimization here. So the Lovász theta parameter of a graph, it's defined as the maximum again of this linear function. So this is the same thing as the trace. Okay, so this is the trace of j times x. All right. Provided you're choosing symmetric matrices which are zeros for the edges and that have trace 1. So they have free diagonal and free off diagonal entries, as long as for the edges you have zeros, but then you enforce that the matrix has to be positive semi-definite. This parameter, as it's written there, is a relaxation of an optimization problem that would allow you to compute the co-click number of the graph, the size of the largest independent set. And it's very easy to see that because you can provide a feasible solution for this thing with objective value equal to alpha. Okay, the size of the largest independent set of the graph. And because this is an optimization problem asking for the maximum, then you get the inequality. Okay, and what feasible solution is that? Well, simply pick z to be the characteristic vector of a co-click. So z is a vector with 1 zeros, and so on, right? And the ones are precisely identifying the vertices in a co-click. And then if you write the projection onto this vector, zz transpose, and you normalize it, this thing here has trace 1. It is a projection, so it's positive semi-definite. And it's not difficult for you to convince yourself that the ij entry of this thing, if ij is an edge, is equal to 0, because an independent set does not contain an edge. So this matrix here satisfies these 3 constraints. And if you compute j times this matrix and you take the trace, the result is alpha. So this thing here is a feasible solution for this thing with objective value equal to alpha. And therefore alpha is less or equal than this guy. Okay. Now, what happens if instead of, and actually it's a nice result, or it's a nice thing to observe if you're studying SDP, that if you add the constraint that the rank of x is equal to 1, then so this is the sort of a constraint that is not allowed if you're trying to solve an SDP, because then it no longer is efficiently computable. Right? Anyway, now what if instead of only one independent set, I'm actually allowing myself to use or to look at several independent sets which are all disjoint? Because after all, coloring a graph is the same thing as picking a bunch of independent sets, okay, which are all disjoint. that cover the graph with the minimum number of independent sets, right? Which are called color classes. Okay. So what if instead of only one independent set, I actually allow myself to use k independent sets? So imagine that you have k independent sets. They're all disjoint, and the characteristic vectors of these independent sets are called Z1 all the way up to Zk. Okay, so I have k characteristic vectors here, and I write the matrix, which is the sum of the projections onto these guys. So that's basically the same thing that I did here, but instead of only one independent set, now I'm summing a bunch of independent sets. And if you want to visualize this matrix, this is a matrix with a bunch of blocks. These blocks have a bunch of ones, and each one of these guys, so this is independent set, this is independent set, and so on, right? So a bunch of independent sets on the rows and columns indexing the blocks of ones in this matrix. So this is exactly what this matrix is. And I am allowing myself to use k blocks. Okay. Of course, if I manage to cover the graph, I have a coloring. But if I don't, I'm simply trying to find the maximum number of verses that I can cover with k independent sets. Okay, that's a nice question. And it's basically what sits between alpha and key, in a sense. Okay. And it's not difficult to convince yourself that if I take the product of this matrix with J and compute the trace, I actually get the total number of verses which are being covered by these coclicks. And what do I need to change here to allow X to be one of those matrices? Well, it's actually quite simple. I still have that this X here, some of these matrices is missing the edges. Right, in that drawing that I put here, all these blocks are independent sets, right? And the edges of the graph are actually here. So this is a zero entry corresponding to the edges. Okay, because this is independent set, so there are no edges here, no edges here. All the edges of the graph are outside of the blocks. Okay, so I still have that this matrix Z is missing all the edges of my graph. Its trace is no longer one, it's now k. Because each one of these guys has trace one, and I'm adding k of these guys. But to prevent the upsetting possibility of simply getting one solution here and multiplying this solution by k, I now enforce that this matrix X has to be, its largest eigenvalue has to be 1. It sits between I and 0 in the order of positive semi-definite matrices. These projections are all orthogonal. The largest eigenvalue of this matrix is still 1. It's 1 for each one of the projections, and they are orthogonal projections. Okay. So I put k here, but so that I don't have the I cannot simply take one solution from the previous and multiply it by k. I sort of like normalize, kind of squeeze these things between 0 and I. Okay, and I will call this optimization problem, which is still an SDP, var theta k. And this was introduced in the 80s by Mumber and Narasimhan. I actually don't know much about these guys. I know that, well, a simple Google search on their names doesn't return many other results. This parameter was studied again in '95 by Alizadeh, which basically pointed out some basic properties of this formulation. But then recently in 2 papers, 2020, 2021, Renato Soturov and co-authors, different sets of co-authors, studied this parameter quite a nice way. I mean, proving a bunch of properties, basic properties, extending known results for the Lovász theta number. It's a very nice pair of papers. Okay. And so what exactly? And okay, and also in '93 we have this also exploring this definition of this theta k. Boyan, Mohar, and Pojak, they observed that a very similar thing to what we were looking at in the beginning kind of happens with this guy. Why? Well, you want to cover your graph with co-cliques. So of course, I mean, this thing here is a relaxation of the problem of asking how many verses can you cover with k co-cliques. Of course, you can cover your graph with key co-cliques, the chromatic number. So it follows that if I put key here instead of k, this thing is at least the number of verses in the graph. And it's actually not difficult to see that equality holds. So if you put key here, the result is n, the number of verses in your graph, or at least n, just to be elementary. Okay. So of course, if this thing is smaller than n, it must be that this guy is smaller than key. It kind of resembles a little bit what we were discussing before with the sums of eigenvalues, right? And this was actually the point that we asked ourselves, what is the connection between these two guys, right? So we do have that if k exceeds key, oops, if k exceeds key, then var theta k is greater or equal than n. Therefore, the minimum k for which this guy exceeds n is less or equal than key. Okay. And now the final connection is this result due to Chi-Fan. So this is old result. This is from the 50s, I guess. It says that the sum of the largest eigenvalues of any matrix, the sum of the k largest eigenvalues of any matrix can be formulated. Oh, there is a mistake here. It's supposed to be I. The sum of the largest eigenvalues of any matrix can be obtained as the optimum of an SDP. Is the maximum of this product over all matrices of trace k, which sit between 0 and I. So this thing kind of is sort of like trying to behave like a sum of eigenvalues. And then suddenly here we have that there's the minimum case so that the sum of eigenvalues exceeds n, lower bounds key. And we are asking questions about the minimum m so that there's sort of sum of eigenvalues is non-positive. And there ought to be a connection between these two things, and there is. So yeah, so these are remarks, right? So this guy wants to be a sum of eigenvalues. It has a connection with key, and we're asking questions about when a certain sum of eigenvalues is less or equal than 0. So what is the connection, right? What is the connection between these two things? And then, what is it? So in Hoffman's proof of this fact, he applies interlacing to a vertex-weighted version of the adjacency matrix. If you go there and you read Hoffman's original paper, when he's proving that whenever n exceeds key, you get this inequality, he's basically applying interlacing, normal interlacing, to a vertex-weighted version. He actually weights the adjacency matrix with the entries of the Perron eigenvector. That's the trick to deal with the case where the graph is not regular. Okay, so putting weights on the verses of the graph kind of makes sense. So basically, we realized that we had to look to the vertex-weighted version of this k variant of Lovász theta. Okay, and the correct way to do that is to replace the matrix J that was sitting here by the projection onto the vector that you obtain if you get your vertex weights and you take the square root entry-wise. So this means putting vertex weights in your graph and then taking the square root entry-wise and then writing this. Okay, so it's not really a projection if the entries of W don't sum to 1, but it's a rank 1 PST matrix. Okay, and this was not our idea, of course. I mean, this has been done for the Lovász number of the graph, and very nice paper actually shows how to compute the chromatic number of perfect graphs from the 80s, I think. So putting vertex weights and exploring the connection between SDP and graph parameters has been done before. It's the only thing that makes sense here if we want to compare this var theta k and this HFG, because in the proof of this HFG, vertex weights have to be used. So, right. And then this is our result. Our main result is to show that this HFG is less or equal than the minimum k, so that for all possible vertex weights, this optimization guy exceeds this guy. And then, of course, if you replace W by the all ones vector, then we are exactly recovering that H of G is less or equal than this thing here. Okay. This has to be true for all W. So basically, you're asking what is the minimum K that guarantees that for all W this holds, right? And then we proved two things. We proved that, and then we proved that for all W, this minimum K is less or equal than key. So we proved two things. I won't really comment on the proof of this thing because it's slightly more technical than what 10 minutes allow me, but I will comment on the proof of this fact here, because that's actually the part of this thing that I'm mostly interested in. But then, simply by looking at this inequality, we asked a bunch of questions. I mean, does equality hold? It could be. Actually, a first draft of this paper wrongly claimed that equality held here, but we quickly spotted the embarrassing mistake. Fortunately, we still have the less or equal, which is what we want in the end. But I mean, the fact that the original, the fact that we proposed the wrong proof does not mean that there is not a correct proof somewhere else. So this is a question: does equality hold? Is there some polyhedral theory associated with this thing? I mean, can we actually, does this provide any help in computing this guy? I mean, this thing here can be certainly computed somewhat efficiently, but can we improve? Actually, not so much. I mean, there is a question. I mean, can we actually compute this efficiently? And if we can, does this provide any light on how to compute this guy? Okay. Yeah. So this is the two theorems we have. These two inequalities. This inequality is actually the one that I will sort of sketch to you guys here quickly. So so this one is a sort of half a page towards 1 page. 1 page long proof verifying certain, I mean, computing things with positive semi-definite matrices. This thing here, once you have the right ideas, is more simple, as it's often the case in mathematics. So what is the, how can I sketch the proof here? So this is saying that for all, that the minimum K, so that this is true for all W, is less or equal than this. I will prove that the minimum K, so that this is true for W equal to the all ones vector, is less or equal than this. Of course, the minimum K that is true for all W could still be larger than the one that works for the all ones vector, of course. But the same proof works basically, as long as you adjust in the middle. So what is the sketch here? The fractional chromatic number is the maximum of this linear program. So this is the relaxation of the integer program that computes the chromatic number of the graph by selecting independent sets to cover the verses of the graph. Okay. So what is this doing again? This is Y as a vector of variables that indexes independent sets. And in a dream world where P is equal to NP, Y is a 0, 1 vector. Okay, and it's 1 if you're selecting the independent set, 0 otherwise. And then basically this matrix N has vertices as rows, co-cliques as columns. So this vector Y is selecting columns so that when you sum the columns, you cover all vertices of your graph. Okay. Now, unfortunately, Y here in the option of this thing tends to be fractional. So you're going to have some fractions given to independent sets and therefore fractional color. Actually, even computing KF is difficult because this matrix is too big. I mean, given a graph, unless the graph is bizarrely dense, you're going to have an exponential number of independent sets, and you cannot actually even write this matrix efficiently. But anyway. Now, what am I going to do with, so what do I want to do? I want to show that the min k, so that this thing here is greater or equal than n, is a lower bound to the fractional chromatic number. So I'm going to start with a solution for the fractional chromatic number, and I'm going to provide a solution to this guy with objective value at least n. And this thing here is going to be Kf. Okay, so this is what I'm gonna do. So what solution is this? It's going to be the sum over all co-cliques of the graph of the weight given to this co-clique by the optimum solution here, y, times the projection onto the co-clique. So this is a matrix that contains, it's a weighted sum of block matrices whose blocks correspond to co-cliques. And then it's not difficult to see because this is a sum of projections onto co-cliques that it misses all the edges of your graph, because y transpose 1 is equal to Kf. The trace of this matrix is equal to Kf. This matrix, the sort of like more difficult thing is to show that, well, the fact that this matrix is positive semi-definite is quite immediate. The harder thing here is to show that this matrix is, its largest eigenvalue is equal to 1. It's not difficult, but it's the trickier thing. And recall, so this is for W equals 1. I claim that actually by varying something here, you get a proof that works for all W. Okay. And it's not difficult to see that the inner product of this matrix with J is equal to N. So the conclusion is that N is less or equal than the maximum over all the inner products of matrices satisfying this constraint. And therefore, the min K, so that this thing here is greater or equal than N, is at most Kf. Now, Kf could be fractional. And I'm sort of like ignoring this fact because this is not a problem. I mean, this semi-definite program works if you use any number here. It doesn't have to be an integer. Okay, but if you want to use an integer, simply put a ceiling here and you're good to go. And it's easy to see that if you allow this thing here to vary, it's sort of like monotonic with the optimum of your program. I mean, there's no way I can increase this guy and have this become smaller. So if you put this thing here, you're good to go. But anyway, so this is the proof that shows this inequality. I mean, we have to use all W because if we do not use all W, we cannot show this inequality. So this is a sort of like the difficult thing here. We are able to show that this guy is less or equal than this guy because we can squeeze in something which sort of like works as a cushion. Okay. So what is there to be done? Well, a bunch of parameters which sit between the clique number of the graph and the chromatic number of the graph. David Robertson knows way more about these parameters than I do. But it's been shown, well, we realize that this guy is greater or equal than the ceiling of the Lovász theta of the complement. We showed that this guy is less or equal than the fractional chromatic number or the ceiling of the fractional chromatic number. And Wokshan, Elphick, and Arbare show that this guy is less or equal than the quantum chromatic number. So, for example, there is a third parameter called the orthogonal rank. The connection between these two things is not known. And there is this projective rank of the graph, which lower bounds these three guys. And actually, we ask, what is the connection between these two things here? So this is one question currently open. We left it open. Yeah. Okay. Another line of research is how to optimize eigenvalue bounds in general. I mean, there are a bunch of papers about eigenvalue bounds. I mean, if you simply, I don't know, Google eigenvalue bounds to chromatic number or any other thing, you're going to find a bunch of results. Most of the papers do not try to optimize the bounds, and actually we have realized that many of these bounds actually fall into the same framework. I mean, there have been papers that have published eigenvalue bounds to things, and other paper goes there, publishes another eigenvalue bound to another thing, but those are actually the same eigenvalue bound if you cast into a framework that you allow some matrix to vary, okay? And then, of course, we should be asking the question, how to optimize eigenvalue bounds in general. I mean, some of these things are very hard to optimize. For example, if you look at inertia bounds, then it's sort of a consensus that you cannot really cast into a semi-definite program framework, but these other eigenvalue bounds can, right? I mean, when you start looking at sums of eigenvalues, I mean, hidden somewhere there should be a SDP or at least some SDP that connects to it, as we have observed. Another connection is that, well, Hoffman used interlacing to a weighted version of the AGT matrix to prove his lower bound. We have realized that there is a sort of like, if you look at interlacing, the proof of interlacing, at some point you request the matrix S to satisfy S transpose S equal to the identity. And hidden somewhere in our work is the fact that if instead of requesting S transpose S to be equal to the identity, but instead S transpose S to be less or equal to the identity in the positive semi-definite cone, you still get a version of interlacing, which is a sort of fractional version. And therefore, we are wondering for what other applications this hidden interlacing, fractional interlacing works. I mean, it's not as trivial, or it's not as immediate how to apply interlacing in most cases, but this is a question we have. And we also would like to know more properties about this kth Lovász function of the graph. There's got to be some duality theory with this guy. So, for example, key is, sorry, this is lower bounded by this thing, and alpha is upper bounded by this ratio. Both these things are likely due to Hoffman. This one is also, I mean, Lovász explored this quite heavily in his works. These bounds are actually jewels in a very formal sense, using, I mean, it's also a result of Marcel and I in a third co-author in another paper, that there is a duality theory in convex analysis that actually guarantees that, I mean, sets these two bounds in the same framework and shows that they're jewels. And we are wondering if there is a similar duality theory for this guy, and therefore a sort of a dual parameter to this h of g that we define here. So this is also something we believe could be a line of work. And that's it. Thank you very much. These are my co-authors.
Thank you, Gabriel. Okay, so is there any questions for Gabriel?
I have a question.
Go ahead.
So everything froze for a second. I have a question.
Yeah.
Is the ceiling necessary?
Otherwise, the range comes in.
Yes. The ceiling, well, okay, necessary. If you're asking necessary, do I have an example? No, I don't have an example. The proof doesn't work without the ceiling, but it works if instead of, let me just, yeah, if instead of summing these guys, you replace this by the, oh, look at who is here. Is he learning SDP, David?
Yeah, he's an expert. He doesn't need any help. So don't worry about it.
Good, nice. Anyway, the same thing works if you replace this thing here by, you look at Kai-Fent's characterization of sums of eigenvalues, and where is it? Yeah, if instead of asking, if instead of putting sum of eigenvalues in nature of G, you put this thing, and here this doesn't have to be an integer. So this is the way of a fractional sum of instead of summing eigenvalues.